Recording. Wait, okay, let's see. Can you guys hear me?
Yes.
Yes.
So I'm trying something a little strange. I've got my phone on. Just in case we have these problems we had last week. I think I know what happened. I think I know what was happening, but I'm not sure. Um, Gosh, what I don't see on my phone is a way to turn on and off the sound, which is odd. Go away. I find that very odd. I find it very strange that I have no way on the phone. Have any of you used the phone app for Zoom? Like it used to show me like a little microphone thing I could turn on and off, but I actually don't see that option, which I find just odd. Okay, let me see if I turn my phone screen off. Can you still hear me? Okay, good. So we'll see how this goes. So I'm using these to talk through. So also if that starts breaking up, let me know and I'll switch to something else. But this way, if my computer freezes, at least I'm still here on the phone, and maybe we don't have to like completely stop. So I'm still letting people in. And I think I'm also here as co-host. So I think this version of me can share stuff. So I think you can see my screen now. Is that right? Sorry, just
Yes.
different things going on. All right, good. Let's see. Are we missing anyone? How many people do I have here? So 1, 2, 3, 4, 12, 14, 15. Looks like maybe everybody's here, I think. Okay. Good. All right. Let's see. Before I start, do you guys have any questions? So one thing about this week, right? Next week is the exam week. I think all of you, except maybe one, has chosen your project topic. So hopefully that's going okay. And remember, I'm going to let you have until the end of next weekend. So that won't be due on Wednesday, right? That'll be due at the end of next weekend. So you'll have some extra time. The exam will be due next Wednesday. Okay. So I will get that exam posted on Thursday, and it's all take home. Some of you have had my classes before. The exam is, because it's take home, it's non-trivial, right? There is a true false section where you need to give me explanations of why things are true and false, right? Then there's long answer sections. And in the little note that I gave you, I do have to watch out for people just popping in answers from AI, right? I don't want to see that, right? I don't mind you using it. Obviously, I use it. You can use it to learn from, but I don't want your answers to be copied from it, right? So if it looks like an AI answer, if it sounds like an AI answer, right? If it looks like a duck and quacks like a duck, I'm going to think it's a duck, right? And so I'm going to ask you to verify that you actually know what you're talking about, right? So one thing I would strongly suggest is just using stuff that we've actually talked about in class, right? So don't go off and grab extra things that we have not looked at unless you're willing to get on a phone call with me and verify that you actually know what those things are, right? Because that's sort of the biggest giveaway. That besides that and the formatting, right? Like if you give me something with a lot of bullet points, and words like next we will do this and if it just starts not sounding like a student, right? Anyway, you all teach, you have to deal with this stuff. But maybe you don't teach math where you have to have people doing proofs and things like that. So I mean, math is a little easier maybe in this sense than language classes are, right? Anyway, any questions about anything to start with? Any
I do want to
homework?
clarify. Yeah, I wanted to clarify, we don't have to submit an outline if our topics are already approved, like that the outline was approving our topic.
Yeah, for most of you, I just approved the topic, right? So one of you, maybe it was you, sent me a little outline. Somebody did. So yeah, that was fine. But mostly I just approved the topic itself.
Because it says there's an outline due on June 25th.
Oh, it does? But yeah, so forget all the due dates for the thing.
Okay.
Where does it say that?
That was more in the link where you list like everything, like where the homework is. Because there's also a typo on there too. It said the exam was due June 12th. And then it talked about us submitting corrections by like April 20th.
Okay. Okay.
So I figured
sort of
I figured that was
yeah. So one thing I've done is I've used that sheet over and over. So sometimes I change the
right.
dates and things, they don't actually get changed correctly. So here, help me out with that. So let's see, we're going down here. And this is our first test to see if things stop working. So that's this week.
Right there, exam one. So if you go where it said exam one. Yep. So it says due 6/12. Okay. And then even in there it said to submit the reflections by the following Sunday, 4/20, which I believe should be Sunday, 7/6.
Okay, so exam one should be due 7/2. I don't really know where the 6/12 came from. That's weird.
That make the project due date still the 7th, like a little later, like you had said as well? Or,
so project
6th. Sorry, the 6th, I guess.
Oops. Hold on. Project due date will be the 6th.
Which is after it says online.
Oh,
like
I see. Okay. Yeah, so you'll see it. It'll probably give you a little red box that says something's not turned in. You just have to ignore that. I want you to concentrate on the test first, obviously, right? I mean, they're both important part of the grades, but first test, then project. And you can work on them at the same time too. But once I give you the test, I want you to be able to concentrate on the test. Let's see. Another thing about the test. So let me stick with the test for a second. If you're typing stuff up, I probably would actually. I mean, I do kind of like grading the PDF. So it's fine if you give me a PDF because that's easy for me to grade. But it's also easy enough for me to generate PDFs usually. Like if you just give me a Word, right? I can just make a PDF out of it. I would kind of like the source file for that. That would be nice, especially those of you who maybe embed images, right? So I get really suspicious when I get a PDF, which is really a bunch of pasted images in there, because that starts looking a little bit strange, right? So I would like to not see that, right? Especially that, because even with a normal PDF, I can see if the words are individual words or if they're pasted images, right? So I don't really want to see pasted images. But if you have the source, you can give me both, or you can just give me the source, right? Especially if it's like Word or something like that. Okay. How many people are actually using LaTeX? Is someone using it? Where is Hannah? What is Hannah? Can you speak? I'm not sure I've ever actually talked to you, except maybe the first day. Are you actually there?
Yes, I'm here.
There we are. Do you use LaTeX? Because your stuff always looks like it's LaTeX.
Yeah, I just, that's what I've normally used. That's what I have been using.
Okay, so you use Overleaf or what?
Yeah, I use it through Overleaf.
Okay, so I mean, an option there would be to share your Overleaf, with me or something like that, right?
Yeah, I can share like the actual like tech file.
So the tech file can be tricky because it depends. Like if I were to share my tech file, you would also need all my header files and stuff. But from Overleaf, you can also share the project itself if you want. But anyway, send me a PDF,
Okay.
but then share the LaTeX with me. Okay, good. Okay, and I guess that maybe you're the only person doing that. Everyone else is using Word, or many of you are writing, just scribbling stuff, right? I say scribbling. I scribble, obviously, right? So that's what I'll call writing. I think writing is probably supposed to be good for your brain. Okay. Yeah, you can tell me when I got dates wrong, because yeah, obviously those two are wrong. Let's see. In the test, be thorough. Don't spend a lot of time doing things like showing that 5 is prime, right? I mean, it's a little hard to say what things are needed to be thorough with and what things aren't. So it's a little bit of a learning curve. But things that aren't sort of obvious, right? Those should probably be spelled out, right? And if you're using something from the text and you're going to use it, you should probably let me know you're using it. And you should use only stuff that we've covered. You shouldn't use stuff from chapter 24, right? Or something like that. Somewhere later in the text, it says this thing you're asking me is true, right? That's probably not what I'm wanting to see, right? Make sure if they're a hypothesis that you're using them, right? Probably if there's a hypothesis and you're not using it, you're not doing something right. And that's kind of like a sanity check, right? Make sure if there's an if and only if proof that you're proving both directions, stuff like that, right? Make sure if you're making an assumption, you spell it out. Anyway, stuff like that, right? So I've sort of warned you that the only real looking at your work that I do is at the DQs, right? I mean, I've been leaving it up to you to sort of look at your own homework, right? Pretty much you're getting that grade for turning it in, but I don't have enough time to to actually grade it all. So this will be the first thing that's really graded. The other thing is there's 16 of you. And even with just 4 students last semester, it would take me many hours to grade 4 exams, right? It'll take me many hours to grade all of these exams. So it might be a little while before you get them back. Just a warning, right? I'll give you the solutions right after you turn them in. Like as soon as I have everyone's exam, I'll give you the solutions, and then I let you do corrections for some amount of points back. I forget what I said. I may have even said 50%, right? Quite a lot of points back. Those you can get immediately, and you have your copy of your stuff, and the idea is you're supposed to look through and see where you got things right or wrong and make corrections, right? The actual TF mark, right? Those points you won't get anything back, right? Because if you have a T and you change it to an F, that'll stay fixed. That's like each true false question is worth 10 points. So those 5 points for having the wrong T or F will stay lost, right? But the points for the justification, right, you can get half of those points back, stuff like that, right? Okay. And And I won't give you my feedback until I have your corrections, right? I don't want you to just look at what I say and make those correct. I want you to sort of take it, look at it, think about what you did wrong. Even let me know why you did it wrong, right? If that's if that comes up, right? Because I think it's useful for you and it's useful for me to see too. I mean, for both of us, right? And if you want, you can give yourself a score. I mean, sometimes your chances are many of you will be faster than I will because you're going to be doing this for your paper, not for all 16 of your papers, right? So, you can give me a score. It's always interesting to see when you give me scores. Sometimes you're tougher on yourselves than I am. And then for the project, just to make sure we get this, right? So there should be a set of slides. There should be a video, right? And it shouldn't be aimed at me, right? It should be aimed like you're teaching this material to a class, right? And the class might be your own classmates, right? You may pretend you're teaching it to your classmates here, right? At least if you're teaching it to a class, you're teaching it to a class that kind of knows what's going on, right? So you're not teaching it to an Algebra 1 class or something, right? You're teaching it to a class that kind of knows what's going on. And then you should have a video, right, explaining that. And it's usually really important because sometimes the slides I think are really lacking, but then the video turns out to be really good, right? So, it's a good thing to have that video in there. Sometimes I don't even understand what you're doing in your slides, but then when you tell me in the video, you go, oh, okay, now I see what you're doing. Then you should have in the video, in the slides, you should have some examples, of course, not too many. You should have an extra set of like problems. Like if you were doing this in a class, like I'm going to say problems, like if you were going to give homework or if you were going to give them some sort of thing to do as a, what do teachers call it, like an exit ticket or so, some stuff for the students to do on their own, right? Outside of the slides and video, right? So something separate that they would do on their own, right? Something like that. Does that make sense? Okay, if you have any questions, feel free to send me messages and ask, right? Topics, right? Whatever it is you have questions on.
I'm going to ask a question because I don't know if someone else has this. So I'm kind of combining chemistry with the algebra. So my assumption is that just minimal of the chemistry and more focus on the algebra of the concept.
Yeah, I don't know anything about chemistry. So I'm assuming you're looking at like chemical structures that
The
are making some sort of
C60,
crystals or
Yeah, the C60 that. Okay. It's
yeah.
okay.
So however the groups are used in there, right?
Right.
However
Okay.
the symmetry groups are used, and whatever the chemists do with that, right?
Okay.
Yeah, I mean, again, pretend you were doing this in a class where no one else maybe knows any chemistry at all, right? You would have to tell them just enough to solve whatever problems you're giving them. But then the main stuff you would expect them to know is the math, right? At least be prepared to generalize whatever math they know together with whatever you're teaching, right? Usually these turn out to be really good. I mean, all of you are teachers and usually you do a great job at these things. So that's sort of what I expect. The exam's a little rougher, right? I mean, students tend to struggle some with the exam. So don't be surprised if you struggle some with the exam. Don't forget you can earn back some points. That's a good thing. Good. Any questions about specific homework that you want to see before we start doing some stuff today?
I have another question about next week. Are we going to be having a quiz next week since we don't have any readings?
No. So, okay, two things about that. So there won't be a quiz. And our meeting next week, there won't be any new material. It'll really be for you to ask me questions if you have any questions about anything on the exam. If you notice something on the exam, right? Because again, I'm typing all this stuff up and I'm doing it I've also got like 120 other students that I'm dealing with too, right? So it's easy for me to make little mistakes, especially on sort of sophisticated questions, right? So if you notice something that seems wrong, don't wait, right? Ask me about it immediately. Even if I'm right, I'd rather you just ask so that I can clarify it, right? Because maybe it needs clarification somehow. But certainly when we meet next week, if you have any questions on the exam or the projects, we can talk about that. And if you don't need to, I'll say it's kind of an optional meeting. If like you're all good and you don't need to meet and you would rather What is next week anyway? Because the 4th is coming up. Yeah, okay. So next week's the 30th, so it's not quite the 4th yet, but anyway. Yeah, so no quiz next week. Good. No questions about any homework or anything? You just want to get right into talking about stuff? We'll see if my
Excuse me.
Mhm.
I just have a quick question. Is there any way that you could possibly post the exam like late Wednesday night so that those of us on the East Coast can jump into it early on Thursday?
I'm not going to promise because when I make promises, I feel bad about breaking them. I can say I will keep that in mind. I will
Fair
try.
enough.
Yeah, but I do have a lot to do before then, and it takes me a long time to make these exams. But I do have more exams. The more I teach the class, the more old exams I have. So, I have more stuff to work with than I have in the past. I've also been writing down ideas for future problems. So, to try out future problems. So shouldn't take me too long to take one of my old exams and sort of retool it for a new one. So I'll keep it in mind. I'll try. Okay.
Appreciate it. Thank
I'll
you.
certainly post in the announcements when I get it out. Okay. And if you want on Wednesday, send me a message to remind me that you'd really like to have it on Wednesday, right? Because sometimes I do get really busy and just forget to deal with things until the due date gets there, right? Good. Okay, I looked at all of your DQ1s. I mean, for example, DQ1s in this class, right? So I looked at all of those today, right? When you probably turned them in a few days ago. So I gave you some feedback on all those things. Mostly what I'm saying looks pretty good, I think. I mean, some of you are picking really pretty simple ones where I think you're giving me the right answer. Just keep in mind that that's not really doing much for yourselves, right? I mean, it's those of you who are giving me questions where you are maybe stuck, right? Or have questions about what you're doing, that's probably better for you, really, right? Because then I can say something maybe useful there. Or even you can talk to each other, right? You can even give each other ideas, right? So that's a good use of that. Okay, good. Let's see. So let's go into a little mini lecture. I do have some videos for things that I've gotten in there. So I have a video for you're seeing my screen, right? Or you're not? You are, okay. So I have a video for the cosets and stuff. So won't spend too long on that because you have that video. Internal products and things. I have another set of notes about products and direct sums and those things. So we'll look a little bit at that. And I put a video in there, right, on some of that material. That's actually a big topic. You might think it's not such a big topic, right? I don't know. For those of you who had 512, you did products and quotients of linear algebras, of vector spaces, right? And it was really, really easy. But it turns out that for groups, it's not so really, really easy. It actually is a big subject in groups, okay? For abelian groups, it turns out to be really, really easy. And the point is a vector space is an abelian group. So it turns out to be really easy, right? But for the non-abelian cases, it's not really easy. Anyway, we'll look at that some. And then we'll look a little bit at the normal groups and factor groups. Okay, we've already looked at homomorphisms, so I'm going to say we've already kind of done the homomorphism stuff. I guess I haven't officially stated the first, second, third homomorphism theorem, but some of you have been using it for a while, and I think I've probably used it in notes already. So we'll see when we get there. Anyway, real quick, maybe I just ask. Someone tell me what a coset is. How do you define it? Like, what properties do they have? Anyone? I'll pick someone.
I mean, they have a lot of properties. There's like 9 properties for it.
Okay, you can list them. So what is it, first of all? What do I need to have cosets? What's the first thing so first I need a group, so I'll give you that one, right? What's the next thing I need?
A subset of the group,
Or something a little bit more than that, right?
subgroup of the group.
A subgroup, I need a group. Okay, subgroup. Okay, now what is the coset? So now this is just a matter of definition. There are many ways of defining this. What would I define to make my cosets?
It's like taking every element in G and basically like multiplying it into that subset.
Okay, so there's two options there. So we could look at some cosets like this, right? So G times H. So remember in our notation here, this means take the element G. So G is a single element, and we're multiplying it by all the things in H, right? So this is just the set of all GH, such that H is in H, right? Okay, this would be what kind of coset?
A left coset.
This would be a left coset, right? So we could also make right cosets, right? And so this would be the set of all HG such that H is in H, right? So the notation's pretty clear. What do the cosets give you with respect to G? Like, what are you actually getting here?
Do you mean like if you put every coset, if you add them all together, they make up the entire G?
Okay, so if I put all the cosets together, right, they give me all of G back, right? So here's maybe H, that's a coset, right? That would be the same as the coset EH, right? Here's maybe some GH, right? So the way we're going to say this is the union of all these things, G and G, is all of G, right?
So coset, it's a partition.
They make a partition. That's really kind of what I'm looking at, right? So that you get a partition. And that's really important, right? Because then you know that GH is equal to G prime H if and only if GH intersect G prime H is non-empty. That's all you need to know. Right? As soon as you know there's one thing in common, you know the whole thing is the same, right? You get a partition there, right? So once I have a partition, it also means I have what? Like partitions are sort of paired up with some other sort of structure. What are the other structure? Or relation? What kind of relation sort of associated with a partition? If you have this kind of relation, you have a
Disjoint
partition.
we talking about
No, I'm looking for a relation on G, right? So in general, if you have this kind of relation, you get a partition. Say again?
I was talking about equal size.
I didn't quite understand that. Say it one more time.
No, I said I was speaking on equal size, the size of the.
So it will turn out here that they're all of equal size. Okay, that's a special case for this one, right? But more generally, we've already seen this for, say, some of the number theory stuff, right? When we have an equivalence relation, we get a partition, right? So when you have an equivalence relation, the equivalence classes make a partition, right? When we have a partition, the corresponding relation is an equivalence relation, right? So equivalence relations and partitions are basically two different ways of seeing the same things, right? It's really important to understand that, right? So here, what's the corresponding equivalent relation? So I have G H is equal to G prime H, right? So there's the equality of these sets. This is going to be if and only if. So what can I say about just G, G prime, and maybe H to say this? I mean, given a G and G prime, what's sort of an easy way to tell that G and G prime give the same class, give the same coset?
G would be in G prime H.
Would it be the
Okay,
inverse?
it's one. Okay,
The
so it's one thing you
inverse
could say.
equals
So
one?
not equals one, but is in H. So I'll just write. I mean, there's two. So basically, what I want, if you just look at this, I could multiply both sides by G prime inverse, or I could multiply both sides by G inverse, right? So that this thing here would be the same as saying G. I'll multiply both sides by G inverse, right? So G inverse G prime H right? That's what I get. If I multiply this side by G inverse, I just get H. If I multiply this side by G inverse, I get G inverse G prime H, right, is equal to H, right? So that's another way of writing this, right? And that's exactly equivalent to saying G inverse G prime is in H, right? So we define this as the equivalence relation, right? So for the left cosets, right, G is equivalent to G prime if and only if, and it doesn't matter which one I take first. So G inverse G prime is in H, right? We saw this before for number theory, right? We'd have like M is equivalent to K mod N, right? If and only if, right, M minus N, is divisible by N, right? So I guess I need to leave myself some room. So N divides M minus N, right? Or if you like, if and only if, let's say I've got N in too many places, M and K, sorry, M divides M minus K, right? So I could say M minus K is an element of Zn, right? Right, and in this case, this Zn, what is it? It's a subgroup of Z, right? So this relationship we have here, this sort of N, oops, I did not mean Zn like this, I mean this one, right? And NZ, right? The products of N, right? Things that are products of N, right? So NZ is a subgroup of Z, right? What are the cosets? The cosets are M in Z, if you like, right? They're products of things, products of NZ, right? This is like, this is like H, it's like G, right? This is like MH, right? So those classes we talked about before for doing modular arithmetic, right? At some point I call them 0 bar, 1 bar, etc., right? N minus 1 bar, right? Well, 0 bar was that subgroup, right? So this would be like NZ, right? And this is like 1 plus, and sorry, I use this notation. I should say here I'm doing additive groups, right? So let me erase that. This is an additive group, right? So this would be M plus NZ, right? So this would be 1 plus NZ. Right, so in the additive notation, this is the way, right? Just to make this clear, right? If our group is additive, right? And I've got a subgroup of G. What are my left cosets, right? They're of the form G plus H, right? Because my operation is plus now instead of times, right? Okay. So in some sense, this is old in the sense that we've done the same sort of thing with number theory already, right? So those equivalence classes in the number theory context, the ZNs, right? They were exactly these kind of things. Let's see, someone dropped out and came back in. All right, so the point is here that our relation G equivalent to G prime, if and only if G inverse G prime is an element of H, right? This is an equivalence relation, right? The corresponding equivalence classes, right, are exactly the left cosets, right? Okay. If you look at the right cosets, right? So I have like HG equals HG prime, right? So that'll be if and only if. Now I multiply on the right by G inverse, right? So G prime G inverse is in H, right? Like that. So that's when they'd be the same, okay? Is it ever the case that the set of right cosets and left cosets are completely disjoint? There's always at least one left coset that's a right coset.
The identity.
Yep. So H itself, right? So it is a left coset, it's EH, and that is HE, right? So that coset is always the same, right? Is it the case that GH and HG, so there's a left and right coset, are those disjoint from each other? I mean, they might be the same, right? If they're different, are they disjoint from each other? I see a head shaking. But what's an element of GH? What's an obvious element of GH? I see mouths moving, but you have to throw in your speaker for me to hear you.
I'm not sure.
Little g.
So little g is in GH, right? Little g is in HG, right? Because E is in H, right? It's a subgroup, right? So it's always the case that if I look at the intersection of these, G is in there, right? Okay. But the left cosets and right cosets, they're no longer partitions, right? They're sort of unrelated in some sense, right? So there's no reason in general that left cosets and right cosets need to be the same, right? So knowing that there's something in there doesn't mean they're the same, right? Because that's not in the, right? If we just look at the left cosets, those are a partition. If we just look at the right cosets, those are a partition, right? But if we look at both together, they're just some sort of collection of sets, right? But it is always true that H is both the left and right coset. So some left cosets may be right cosets. There's always at least one H, right? And it's also the case that they do overlap without being disjoint, without being the same, right? So just sort of keep that in mind. Anything else we should say about cosets? Just what they are, how they behave. I feel like someone said there were like 9 properties of cosets. I don't feel like I've mentioned all 9 yet. Anybody have any questions about just what cosets are, the fact that they're partitioned, all that stuff is good? Okay, what's the one important theorem about cosets?
Lagrange's theorem.
Lagrange's theorem, right? And so what is Lagrange's theorem? Lagrange's theorem. So far, we're not having my thing freak out on me. What does Lagrange's theorem tell me?
Is that absolute value of H divides absolute value of G?
Okay, I kind of like writing it this way. So I like writing that the size, you say absolute value, but really we mean here the size of G, right? Or the order, right, is equal to the size of H, whoops, the size of H times what? Yeah, let me give myself some more room. That's kind of bad. So we got the size of G is equal to the size of H times, and then what do I want to put here?
The index of H and G.
So the index, or I could say the number of cosets, right? And the reason I like this one a little bit better is because if they're infinite, this still makes sense, whereas dividing doesn't make sense, right? So if these things are infinite, this particular version makes sense. And then this number of cosets we do call G colon H, right? Now, this actually doesn't follow immediately from what we've done above. So there is one more important thing that we didn't actually do above. What we get from above is we get that G is being partitioned, right? So we get that G is the union of all of the, how do I want to write this? Well, I'll just write it like this. Of all of the cosets, G and G, right? Now, this is a set, right? So if something appears in the set twice, we really only count it in there as being once, right? So this is saying take the union of all the cosets, right? So if GH equals G prime H, it's only in this set once, not twice, right? Okay, so literally when we put the size things on there, this is a disjoint union, right? We know that these different one of these cosets are disjoint. So when we're taking the union of disjoint sets and we're looking at the size, we can just get to add up the sizes, right? So this equals the summation of GH, where GH is one of these cosets, right? So I'm gonna write it like that. I don't want to say for G and G because writing it like this, then I would be overcounting, right? Because I'd be counting the same thing a bunch of times. All right, so I'm just saying, look at all the cosets and you add up all the sizes. This is just because we have a partition, right? So there's no group theory in some sense yet. In order to get this statement up here, what we need to know is that all of these are actually the same size, right? So how do we know that H is equal to GH? How do we know the size of these two things are the same? What do I need to do to show that two sets are the same size? What's it mean for two sets to be the same size? Like, what does it mean just say X equals Y set size? These may be infinite now, right?
So they have to have the same number of elements.
Yeah, but that's kind of circular, right? Like, what do you mean by number here? I mean, say this is the reals and this is the complex numbers, right? So they're infinite sets, they're really big. Like, what does it mean? Or maybe this in Q's over here, is that the same size or a different size? So there's a way of saying it that doesn't involve the notion of number, right?
Is this where we'd say it's like 1-to-1 or onto?
Yeah.
No.
So if we have a bijection, right, between the two sets, we say they're the same size, right? So we want to show two sets of the same size, we just need to come up with a bijection between them, right? So what's the obvious bijection? Let's say going from H, let's go from H to GH. There's an obvious bijection here. What is it? I'm going to take an H in here. What am I going to map it to?
To G little h.
To G little h, right? And okay, so is this onto, right? So is everything in here represented like this? Of course it is, because it's right. So okay, is it 1-to-1? So is it the case that GH equals what G prime H, right, implies that G equals G prime? Should be a giveaway, right? So what do I need to do? I want to get from GH equals G prime H to G equals G prime. What do I need to do?
Right. Multiply both sides by H inverse.
Yeah, that's it, right? That's the whole point of having inverses, right? I can do that. You can multiply both sides by H inverse. I can always do the same thing to both sides of an equation, right? So this is GE equals G prime E, right? And that is G equals G prime, right? Suppose I was in the world of matrices, why would this argument not have worked? Right? So you should know from your matrix stuff that if this happens, it does not need to be the case that B equals C, right? Generally, that does not happen, right? So we are using the fact that we're in a group, right? So we have inverses, right? We have multiplicative inverses, right? So in order to get this, you have that. But anyway, so this is a 1-to-1 onto map, so these are the same size, right? And since these are all the same size, all I really need to do to get the size of G is count up how many of those blocks are in there, right? They're all the same size. So I have the number of those blocks times the size of H, they all have the size of H. And that's the size of G, right? So that's what this thing up here is. That's Lagrange's theorem. Why is that such an important theorem? What is one thing it allows us to do? And you've already done a lot of this in your homework. It means, say I've got a group G and G has order, and I'll just pick one like from the homework, 21, right? Okay, can I find a G and G such that the order of G is 10?
No, because 10 is not a divisor of 21.
Yeah. So the point here, to write it all, G, the group generated by G, right, is a subgroup of big G, right? And so what Lagrange's theorem tells us is that the size of this thing, which we also just call the order of G, right, has to divide the size of G, right? So now I'm working with finite groups, right? So we're assuming this is a finite group. Oh, I mean, I said this, right? 21 is definitely finite. So that's a given. Good. All right. So here's another thing. So here's another important thing. Why is it the case? So suppose G has size 45, right? And I take something in G, right? Do I know anything about G to the 9 to the 5? So G raised to the 9th raised to the 5 is the same as what? G to the 45, right? And what do I know about that? And why?
Wouldn't that just equal to G?
Not G.
Would that show that G is cyclic?
No, what's just G is cyclic. Am I wrong? Would it be G? No, not G. E. It would be something else.
Oh, E.
I mean, what we know, right, is we know the order of G divides 45, right? So we know that G equals the order of G times something, right? So G to the 45, now it doesn't have to be 9 and 5, but we know that this is G to the order of G to the K.
The identity?
Right? Yeah, so G to the order of G, well, that's E. I mean, by definition, that's what the order of G is, right? So it's E to the K, so that's just E, right? So you always know that G raised to the size of the group for any, this is the multiplicative group, right? G raised to the size of the group is always E, right? How do I write this in additive? Suppose the group is additive, what does it turn into? Because this is like G times G, G many times is equal to E, right? So in the additive notation, right, it'd be G plus G plus plus G many times, capital G many times, is equal to, now what is in the additive case, we write 0 instead of E, right? And there are G many of those, right? So in this case, you would have G times G, right? So G many of those added together would be 0, right? So a lot of the time when we're doing stuff in the class, we use the multiplicative notation, but it's useful every so often to just think about what the additive notation means in these cases too, right? Especially when we get to rings, we'll have to do that sort of stuff a lot. So let's see. So why is this a theorem? M to the phi n is equal to 1. And what's that theorem called? As long as GCD of M and N is 1. And let's say M is less than N.
As Fermat's little theorem.
So this is Fermat's little theorem. And why is it true given what we just did? So saying the GCD of M and N is 1, what is that? What's another way of writing that in terms of group theory? M is in what?
It's not in the UN.
U of N, right? So it's in the units, right? And remember what was a unit? So, I mean, one way is to say GCD of M and N is 1, but what it really means is that M has a multiplicative inverse in Zn, right? That's kind of the better way of thinking about that, right? Because later on, we're going to have this notion of rings, and we're talking about the units of a ring, right? And so you want to think about that, right? This is true if and only if M has an inverse mod N, right? And that's basically this Bezo's theorem, right? And then this thing here, you know, or not this, but here. I mean, this is, and what kind of group is this? It's a multiplicative group, right? Okay, so M is in that multiplicative group. So what we just saw is that M to the UN, size of that multiplicative group, is 1, right? This is our G to the G equals E, right, for this specific case, right? Okay. But then the size of UN, well, that's just what this Euler-Toshin function means, right? So this is M to the phi n equals 1, right? So there's the group theory proof of that, right? Using Lagrange's theorem. So there's other number theory proofs that don't use Lagrange's theorem, but that's the group theory proof that uses Lagrange's theorem. Okay. Good. Let's see. I think I'll do normal subgroups first, and then we'll look at products. So, any questions about any of this? Anything lingering? A really useful exercise. I don't forget if I got one of you to do this or not, but is to go through and look at how to characterize all very small groups of finite orders, right? So it starts getting complicated even at 8, right? But how many groups are there of order 1? Well, there's just one. It's that one, right? They're all isomorphic. You might call it E. You might call it 0. You might call it 1, right? Depends on what sort of notation you're using. But there's one group up to isomorphism of order 1, right? And how many groups are there of order P? So I have G the size of G is P, a prime. What do I know about that group? And you think of a group of order P.
Shouldn't that be like Z to the P or an infinite group?
Well, the order is P, so it won't be infinite, but Z to the P is definitely a group of order P, right? Okay, are there any up to isomorphism? Are there any others, or is that it? And why?
Groups of
What are the only possible orders of elements in this group? So E is in the group. What's the order of E?
1.
1, right? So its order is 1. Is there any other element in the group of order 1?
P.
No, right? Because if like G to the 1 is E, right, then G is to be E, right? Okay, what's the other? So I take some other group that's not E, right? What is its order? This is prime, right?
You have to be P.
It would have to be P, right? Because it would have the order of G would have to divide P. What are the only things that divide P? 1 and P, right? So if I take any other element in the group, its order has to be P, but then G has to equal the entire group, right? Because G only had P elements, right? So the only groups of order P where P is a prime are cyclic groups. They're all isomorphic to ZP, right? Okay, so that takes care of a lot. So that takes care of, so now we have, order 1, order 3, order 5, order 7, right? Now, what kind of groups are there of order 6?
Two and three.
So you, sorry, you could have Z3 cross Z2, that would be order 6. Now we haven't talked about products yet, so I guess we're jumping the gun a little bit. But Z3 cross Z2 is isomorphic to what?
Z6.
It's isomorphic to Z6. And can you tell me why?
Because the 3 and 2 are prime, and if you
That's
multiply.
right. That's right. Because this has this form where this is order 3 and this is order 2. And so you know that the order of A, B, and the product, right, is going to be the LCM. I mean, again, this is jumping ahead a little bit, but it's the LCM of those two things, right? Now, yeah, so I mean, well, under this assumption, that's what you get, right? So that's 6. So if I take this element inside there, right, its order will be 6. And so it'll have to generate the whole group, right? So like that. Are there other groups of order 6? Can you think of another one? It's not this one. So this one, so that one's the same as that one. Can you think of other groups of order 6? You should, because you've studied some already. What have you studied that's of order 6 specifically?
D3.
So D3. And what is D3 actually isomorphic to? So D3 is actually isomorphic to S3, right? So that's the thing you might want to verify. I mean, I know it's in your book already, but this is a group of order 6, which is not abelian, right? Okay, so we know these two are not isomorphic because this one's cyclic, this one's not cyclic, right? This one's not abelian, that one is abelian, right? So there's lots of differences there. A slightly harder thing that I'll talk about in a bit is that these are the only two. Those are the only two possible ones there. Okay. What about 4? I skipped 4, right? So there's two groups of order 6, Z6 and D3 or S3, right? So we have 1, 2, 3, 4, 5, 6. Here there's one group of order 1. There's one group of order 2. There's one group of order 3. There's one group of order 5 because those are primes, right? 6, 7. There's one group of order 7, right? This is just Z7. This is Z5, right? This is Z3. This is Z2. This is, if you like, Z1, right? So just one element, right? For 6, we have two groups. We have Z6, and we have D3, which is the same as S3. Okay. And by the way, Z6 was the same as Z3 cross Z2, right? So those are actually the same. There's only one, right? What about 4? How many groups are there of order 4? So what's one obvious group of order 4?
Z2 and C2.
Z2, yeah.
Okay, so there's one, Z2 cross Z2. That one has a name, so that one's sometimes called V, and it's called Chronikers. It's got a name. I can't remember what the name is right now. But what's another one?
Can you use Z4, Z1?
Or just Z4, right?
Or just
Just
Z4?
Z4, right? I mean, Z4 cross Z1 would be the isomorphic to Z4, right? But these two are different. I mean, remember Z3 cross Z2 is the same as Z6 up isomorphism. Why is Z2 cross Z2 not the same as Z4? What's the thing that's different about those two?
Is it because they're not distinct primes? The two.
They're different. They're definitely. I mean, they're not okay. So the reason that we don't get Z4 from this is because they're not, because 2 is not relatively prime to 2, right? But that's not quite. So this is one of those cases where we're looking for something like, so Z3 cross Z2 is equal to Z6 or isomorphic to Z6 because 3 and 2 are relatively prime, right? I don't want to just say Z2 cross Z2 is not isomorphic to Z4 because they're not relatively prime. I want to actually give a better reason for that. So what is the order of every element in Z2 cross Z2?
The only thing that's coming to mind is you're saying that the Z2 is just 2 order 2s, where the Z4 is an order 4.
Yeah, and that's exactly right. So there's actually 3 order 2s, right? So 0, 1 in Z2 cross Z2 would have order 2. 1, 0 would have order 2, right? 1, 1 would have order 2, right? So there's 3 order 2 elements there, right? And then of course there's E, which has order 1, right? Z4 has order 4, so 1 in Z4 has order 4, right? What is a representation of Z2 cross Z2? There's a couple. I think if you look at the symmetry group of rectangles that are not squares, right? So you have like a flip that way and a flip that way, right? That's a representation of Z2 cross Z2. Also, if you have like a couple of, I can't draw them, but like if you had a couple of light switches that you could turn on and off, that would be right. They could both be on, one could be on, one could be off, vice versa, or they could both be off, right? So that's another representation of Z2 cross Z2. Now, when we get to 8, things start becoming harder, right? So in Z8, you have this, you have some sort of interesting new group called the quaternions, right? That pops in at Z8. It pops in at 8, and as you go above there, well, I guess 9's not so hard because it's 3 squared. We actually know something about primes squared, right? And your book definitely talks about it. Yeah, I mean, actually, yeah. I mean, think about it. What do you know about p squared? This is in your text, right? And you might think, while you're thinking about that, about what happens when you go to p cubed, right? But also when you go to 12, things just blow up like crazy. There's all sorts of groups of size 12, right? So things get more and more complicated. But Lagrange's theorem is a big part of all this stuff, right? So I mean, a lot of it is looking at what orders of things can divide groups, right? So that's a lot of what goes on here. The rest is trying to figure out how you can write things down as products, right? And that starts becoming interesting and complicated when we're doing groups. Okay. Anyway, think about this as you work through your stuff. Think about analyzing groups. Groups of order PQ is sort of interesting. Groups of order where P, let's say Q is less than P or prime, right? Groups of order n times 2, right, are interesting. Like, so like, dn is one of those, right? Does everything have to be sort of a d? And like zn cross z2 is one of those, right? Is there anything else, right? So these are sort of interesting questions. Some of which are in the notes that I have for you. right? But these are the sort of things Lagrange's theorem lets you do, right? I'm just sort of pointing out that Lagrange's theorem is really important, largely for analyzing what finite groups there are. That's part of what it does, right? So that's one of the things it does. It's also really important for, I mean, analyzing what subgroups there are is really important for cryptography and things like that too, right? So this is like, if you look up the RSA algorithm, Fermat's little theorem is a part of that, Chinese remainder theorem. So some of the stuff we've looked at already are things that come up in that argument. Bezo's theorem, right? All that sort of stuff. Okay, let me do normal groups real quick. Sorry. So what differentiates a, so let's ask the question like this. Suppose I want to take my my nice little partition here. So here's my H, here's my G, right? Here's my G, H, right? So there's that partition into cosets, right? And I would like to say, take this thing and I'll make it into an algebra where I say, fine, let AH, BH equal ABH, right? Try to do a product like that, right? Or if you're doing additive notation, it'd be A plus H plus B plus H equals A plus B plus H, right? And have we seen this? Isn't this exactly what we did? We did M plus NZ, plus K plus NZ, all right, is equal to M plus K plus NZ, right? We're doing modular arithmetic, right? So M bar plus K bar is equal to M plus K bar, right? So this is stuff we did a long time ago. So we would like to be able to extend the algebra to the cosets, right? That's what we'd like to do. Okay, so what is the potential problem? So maybe we just try to make that definition, right? When you make a definition like this, one thing you want to check is the definition, is it a good definition, right? So you very often you have this sort of thing. Suppose AH equals A prime H and BH equals B prime H, right? If this is going to make any sense, it had better be the case that that ABH is equal to A prime B prime H, right? Because I'm saying here's two things that are the same blocks up there. Here's two things that are the same blocks up there, right? I want to define this multiplication like this. So these two things had better turn out to be the same, right? If those two things are not the same, we're in trouble, right? Okay. And so now there's a couple of things we can do. Okay, so if I just play with the formula some, I can try to, I guess, multiply both sides by the inverse of this, right? So I can, and what's the inverse? What is A prime, B prime inverse?
B prime inverse, A prime inverse.
So it's B prime inverse, A prime inverse, right? So we can get here B prime inverse, A prime inverse, AB. I'm wanting to show this is true. I don't know that this is true yet, right? So H, right? I need to show that this thing, I guess what I really want to, so here, sorry, let me back up just a little bit. So let's just, if I want to show this is true, it would suffice to show that A prime, B prime, inverse AB is an element of H, right? Because remember that A equals, sorry, let me use a different notation. GH equals G prime H if and only if G prime inverse G is in H, right? So that was the sort of equivalence relation version of this, right? So if I want to show these are the same, I could just show that the inverse of this times that is in H, right? Okay, so let's see what we get. So we get B prime inverse A prime inverse A B, we want to show that that is an H, right? Now, what do I know about these pieces? So what do I know about A prime inverse A? So I know that AH equals A prime inverse H, sorry, AH equals A prime H. Those are the same, right? So that tells me that A prime inverse A is in H, right? So this now what I've got is B prime inverse something in H, B, and I want that to be an H. All right, so now we're in trouble, right? Because basically this is saying I want that B inverse H B equals H. All right, I mean, it takes a little while to think about why those two things are actually equivalent, but they're actually equivalent. I mean, if you like, it's because B inverse HB, this operation here is actually, this conjugation, right, also gives you a set of equivalence classes, but I'll let you think about that. Why are those two the same? But the point is here, this is turning into HB needs to be BH, right? So for this to be well defined, right, in order to take two things that are the same, you know, AH and A prime H are two of the same left cosets. BH and B prime H are two of the same left cosets, right? I want to see that ABH and A prime B prime H are the same left cosets, right? In order to show that, I need to know that the B coset of H on the left and right are actually the same. I need to know that those are actually the same, right? And so it's just sort of working backwards, what we have here is if BH, let's see, the way I'm writing it here, B inverse HB is equal to H, or even a subset of H for all B and G, right? Then my multiplication makes sense, right? Then A, H, BH equals AB, H is well defined. Okay.
Is that a coset property?
Say that again.
Is that a coset property?
Is what this?
Yeah.
No, right? No, I mean, that's part of the point. In general, and you've done exercises already, right? In general, the left cosets and right cosets are not the same, right? B would be in here and B would be in there, but in general, the left and right cosets are not the same, right? They would be the same for commutative groups, right? But definitely not the same for non-commutative groups. Right? I mean, take an example like D, I don't know, D4 or something, right? So what does this consist of? It consists of, you know, E, R, R squared, R cubed, right? F, FR, FR squared, FR cubed, right? Like that. All right, so here's a subset, you know, EF. There's a subgroup, right? EF, because F has order 2, right? So there's a subgroup EF, right? So, you know, subgroup generated by F, right? Is it true that this is that all the left cosets and right cosets are the same? So in particular, is it true that R F equals F R? Right. So RF is R times E is R times F is RF, right? Is this, so there's a question mark here, is this the same as, you know, on the other side, R times E is R again, right? But this would be FR. All right, so is it true that those two things are actually the same? Now they do overlap. They both have R in them, right? Okay, but is it true that RF equals FR for D4, right? And this is not true, right? What is true is that RF equals FR cubed, right? And so those are not the same, right? So yeah, it's not in general true that HB equals BH, right? So HB equals BH is exactly the same as that. So that's important to know, okay? And when this happens, you say that the subgroup H is normal, right? So the definition is H subgroup of G, H is normal in G. And we write that by H. We use this thing that looks like subgroup, but like with a little triangle, G, okay? If and only if, for all G and G, we could say GH equals HT. The right cosets and the left cosets are the same, right? We can replace this. We can just say that GH, G inverse is contained in H, for all G. So we want to show something is not normal. We can just find a single G where this fails, right? If the group is normal, right, then what we just showed is we can create this algebra, right? So instead of just looking at the cosets G mod H, right? So if H is normal in G, instead of just looking at the cosets G mod H, we actually get a group. This is a group. Okay, and the group is given by AH, BH equals ABH. The only thing you need to prove is that that's well defined. That's actually all you need to show. Showing that the rest of the stuff works is easy. I mean, it's sort of an exercise, so I'll let you do it. AH inverse is just A inverse H. Okay, that also follows immediately from the first one, right? Once you know that's well defined. Okay, so you get a new group, right, by taking the quotient group. Okay. When do you know that? So if G is commutative, and H is a subgroup of G, is it true? Oops. That H is a normal subgroup of G? So if it's commutative, right, is it true that GH, G inverse is always contained in H?
Yes.
Yeah, right, because I can just, this is, take an element of there, right? Well, that's exactly the same as G inverse H, right? It's just H. It's definitely an element of H, right? Because it commutes, right? So if it's commutative, so any subgroup of a commutative group is normal, right? So as long as my original group G was commutative, then I can take the quotient by any subgroup. Okay. And often with commutative groups, we use the plus notation, right? And so then we have G mod H in the commutative case, right, is the set of all G plus H, right, where G is in H, right? So our cosets are now G plus H instead of G times H, right, if we're using the additive notation, right? And this is something you should have done some of in linear algebra, right? So when you had a vector space, which was a subset of another vector space, right, you should have taken this quotient space structure, right? And this would be the set of all, U plus V, where U is in U, right? So this shouldn't be completely new, right? I mean, this is something you should have done a little bit in linear algebra. right? And the reason that works in linear algebra is because these vector spaces are abelian groups, right? So everything's working out nicely. All right, so things are more interesting with general groups, right? So when non-abelian groups, things become more interesting. Okay, so kind of get that. So I mean, there's two different sort of things you think about when you see this. You might just think about cosets, right? But in the case that H is normal, you think about this as being a new group, the quotient structure, right? And you know, now I can say without hiding anything that we take Z, we take Z, right, which is Z plus and 0, that the group, right, the additive group. And we look at Z mod NZ, right? This is exactly the group we've been calling Zn, right? And the elements in here are M plus NZ, right? For M in 0 through N minus 1. Right. So we kind of did this the very first day of class. We looked at essentially that kind of quotient structure for this particular case, right? So like, you know, NZ, right? Just to make this one really completely clear, is 0, N, 2N, right, etc. Right? M plus NZ, right, is just adding M to all these things. So 0, N plus M, you know, 2N plus M, right? So all the things with remainder M, right? But this is the sort of thing we're doing. Let's see, so what is one case where you always know that subgroups are normal? So I'm sure I'm not losing everyone. What is one case where you know all subgroups are normal?
When they're commutative?
When the big group is commutative, okay. Another case would be when the big group is order prime, because then you know it's cyclic, so it's definitely commutative, right? It's just good to keep some of these in mind. Another case is when GH has order 2 or index 2, right? So when you have index exactly 2. Why? And this has turned out to be important, right? For example, you know, if I take the group Sn and I look at the alternating group inside there, that always has index 2, right? So there's an example where that's always the case, right? And why is this true? Well, what does our partition look like? It looks like H, right? And maybe GH, and that's all there is, right? So that's like the left cosets, right? What do the right cosets look like? Well, they look like H and HG, right? But the only option is that those two have to be the same, right? So when your index is 2, you're automatically normal, right? So that's an important thing to keep in mind, right? So when we're looking at these like DNs, right, and we look at the you know, so we know the order of this is 2n, right? Well, we know the order of the rotational part is n, right? So we know the index d n index r, right, is 2, right? So we know this is a normal subgroup in there. Right, so that's a thing to keep in mind. And we know that Dn mod R, so now we know this is a group, right, from the construction we just did, because R is a normal subgroup. It's got order 2, so we know this is isomorphic to Z2. Because it's the only group that's, you know, of order 2, up to isomorphism, right? Okay, what's one more important theorem here? Let me just go ahead and erase all this stuff. So it seems like whatever I did is working. It's not freaking out on me today. So what is another group? What is another? So suppose I have, let's say phi going from G to some group K. What were some subgroups? And this is a homomorphism. Whoops. What were some subgroups related to this homomorphism? Do you remember there were two particular ones? One was the image. What is that? Maybe phi applied to all of G, right? It's all the things that come from something in G. And the set of all phi G or G and G. Right. So this is a subgroup. Where do these things live? They live in K. This is a subgroup of K, right? What was the other important one? More important, in fact?
The kernel.
Kernel. And so this is the set of all G, such that phi of G equals 0 or equals E of K, right? And so this is a subgroup of G. Okay, and it turns out that this is always a normal subgroup, right? So let's show that curve phi is normal. And so I want to show, right? Let's see, I actually haven't thought about this. I want to show that G curve phi G inverse is contained in the kernel of phi, right? So that was one of the equivalents, right? So I can show that. Okay. And now what would it mean to show this? I need to show that if I apply phi to G, oops, go away. If I apply phi to G and then something in the kernel of phi, let's say I take some element H in there, right? I need to show that that is equal to E sub K, right? So that's what it would mean to say that this product is in the kernel of phi, right? But this is a homomorphism, so this is phi G, phi H, phi G inverse, right? But H was chosen to be in the kernel of phi, right? So this is phi G. So this is just E of K, and this is phi. Now phi of G inverse is really phi of G inverse. So we're using some properties of our homomorphism there, right? Now the E can just go away because it's the identity. So this is phi G inverse, right? But this itself is E of K, right? So we do get what we wanted there, right? So when I take any element in G and I stick an element of kernel phi between it, and then put G inverse on the other end, well, that thing itself is in the kernel, right? So we have here that the kernel of phi is a normal subgroup of G. Okay. So this means I can form, is there any question about that? You should go through and verify it again. So kernels are kind of the main thing, right? They're sort of the main examples of normal subgroups. I mean, actually, yeah, let me do this as a separate thing. So along that line, suppose I form G over N. Sometimes for normal subgroups, we'll call it N to make sure it's normal, right? Then I can consider this map. G goes to Gn. So I'll call this thing phi N. And what it's going to do is phi N of G is going to be, G N. It's just going to map G to its corresponding coset, right? So here's a claim. Phi n is a homomorphism. So one, phi n is a homomorphism. Two, phi n it's actually one-to-one and onto, so it's an isomorphism. Well, it's not, sorry, not one-to-one. It is onto. Let's be a little bit careful about what I say there. And three, the kernel of phi n is n. Okay. So given any normal subgroup, I can come up with a homomorphism whose kernel is that normal subgroup, right? So why is it a homomorphism? So phi n of a, let's say g n g prime n. So what is this? So this is, sorry, let's try that again. Phi, brain wants to, I want to write something with my hand before I think it in my brain. G prime, right? What is that? By definition, it is G prime n, because that's how I'm defining the map, right? But this we know is Gn G prime n, because that's our definition of product in the, in G mod n, right? And this is phi G prime, right? So in other words, phi preserves product, right? Same kind of argument for inverse, right? Same argument works, right? So phi of G inverse is G inverse n, right? By definition or by checking, this is G n inverse, right? And that is phi G inverse, right? So this phi is a homomorphism, right? When do we get, so what is kernel of phi? Kernel of phi n, right? When is G in the kernel of phi n? So this will be if and only if phi n of G, which is Gn, is equal to the identity of G mod n, but that is just n, right? That is the identity there, right? It's E n, if you like. But this is if and only if, G, well, this is if and only if G is an n, right? The only way Gn can be equal to n is if G is an n. That's part of the being a partition, right? So in particular, the kernel of phi n is n, right? So given any normal subgroup of any group, I can write down this specific map whose kernel is exactly that n, that normal subgroup, right? Let's see. So this is the definition, right? So the kernel, well, I mean, that's what this says here, right? Given any homomorphism, I show that the kernel is normal, right? So given a homomorphism, G2 sum k, right? We show that the kernel is normal. So I can make this map G to kernel phi. Actually, I'm gonna do it like this. So this is something you see a lot in algebra, these kind of pictures. So I've got phi, a homomorphism from G to H. I can make my map G to kernel phi. This was the one I called phi, cur phi, if I like. Okay. And I claim I can get a new homomorphism right there, which maybe I'm going to call psi. Right? And psi of something in here, so G cur phi, is just going to be phi of G, right? So sort of you define it the only way possible, right? To make this commute, right? So if I go in this direction with an element of G and then in this way, so if I go that way, then it's got to be the same as doing that. So we say this diagram commutes. So this is literally what it says right there, that this diagram commutes. So this is so what do I know about phi? So phi is the homomorphism, or psi. Psi is a homomorphism. It is a one-to-one homomorphism onto the image. And you must have been wondering how these were related, right? The image of phi. Okay. So filling out this picture a little bit more, what I get is this. I get that this goes onto the image of phi. That's sitting there as a subgroup of K, right? And this is actually an isomorphism between those two things, between G kernel, mod kernel of phi and the image of phi. Okay. And who knows what this picture that I just drew is called in the book? I actually asked one of you to do these for your project. I don't think anyone took the bite. This is the first isomorphism theorem, right? And we're going to use this theorem. So first of all, this is a really important theorem. These kind of theorems generalize to all algebraic structures. So we use, here it is with groups. We're going to use it later with rings. In some sense, you used it earlier with linear algebras. We'll use it with fields. If you study other structures later on, modules or something, you'll use it with modules. It's a very sort of generic kind of theorem, this first isomorphism theorem. And we'll use it for all sorts of things. Let's see. So here's an example. Let's take Z mapping to Zn, right? Where the map phi of K is equal to K mod n. Right, so now I'm thinking of Zn as being just the number 0 through n minus 1 with that funny algebra, using remainders to define the algebra, right? Okay. Now let's look at what the first homomorphism theorem told us. Well, this will map to Z mod the kernel of phi. What is the kernel of phi? The kernel of phi is just in Z, right? Which things get mapped to 0 are those things which are multiples of n, right? That's the kernel of phi. What is the image of this map? Well, it is everything over here, right? Zn, right? And so what is our first homomorphism theorem tells us? Isomorphism theorem is that there's an isomorphism between Z mod ker phi, so this is Z mod nz, right? And the structure up here that we defined was, say, the truth, the addition table, right? And the map is just taking, what is the map? It's taking m plus nz is getting mapped to phi of m, right? Yeah. So this is like something I did in the first day of class for these ZMs, right? And now we have all the theory to say, this is what we were doing, right? So this is, sort of circling back to day one of class, right? This is kind of what I had in mind when I said, there's this way of representing the structure, there's this way of representing the structure, and later on in the class, we'll see that they're both exactly the same, right? So this is what I mean by saying they're both exactly the same. I mean, they're isomorphic, right, in this sense. We will use this third isomorphism theorem for lots and lots and lots of stuff throughout the class. So try to take it and understand what it says. It's a really sort of important, theorem. So let me just write it one more time in slow motion. So again, I just have a G, I have a homomorphism, phi going to some H. Well, in fact, let me just make myself some more room here. So it definitely goes to, the image of phi. We know the image of phi is a subgroup of H. We know that, right? And now we're saying what happens here is I can go to G mod the kernel of phi. This is an onto map. So this is the one I called phi ker phi. And then we get this map filling in this way, which is called psi, right? And this is going to map G ker phi is going to be mapped to phi of G. That's really the only thing you can do, right? That's where it has to go. And this turns out to be an isomorphism there. Right? So this is onto the image of phi, right? That's what it means to be the image of phi, right? So those are two onto maps. This turns out to be an isomorphism between those two things. So this is a way of generating isomorphisms given homomorphism. Okay. And the fact that if you go this way is the same as going that way says the diagram commutes. I think there's two. Right? So sometimes the theorem would just say, here's a picture and the diagram commutes, and that's the theorem. Right? That's sort of the way these work. And so we'll see plenty of these like commuting diagram type stuff. This is quite a bit. Let me just see. I mean, the products, that's another thing. Let me just take a break here for a second. Is there any, have you thought of any questions you want to ask me about any homework or anything you've been stuck on? So what is the one thing I haven't done yet is I haven't actually talked about products yet. Okay, so let me say a little bit about this. So here's in the notes, in the mini lecture notes, let's go back to here. I've got a few little notes about products, but I say go to these notes and there's some more notes. And so that's, I'll just click there, so click there. And so here's the sort of general notes about products, and there's another video I put there about products. Okay. So I don't want to do everything in this product section. I'm not even sure how much more. I mean, we've only got like 20 minutes. So I'm tempted to say we might be at our cognitive load limit at this point, because we've talked about a lot of stuff. And I may say, maybe just go watch the video, okay? There is some stuff toward the bottom. Some of you are doing this. There's actually two. Okay, let me point to two things. Maybe there's one little thing I want to say a little bit. So I do talk about finite products and sums. Finite products and sums are the same. Okay, there's no difference. When you go to infinite products and sums, they're different. Infinite products have something entered in for every single element. And sums only deal with finite and many at once. So I'll let you read the definitions. And I've given you a couple of interesting examples here to think about. Those are the external products. That's where you just take a G and an H and you make a product. That's really easy. For the internal products, the difference is, oops, someone's popping back in here. So for external products, you have an H and a K and you just build H cross K. Okay, that's a really simple construction. For internal products, it's different. You have a G and you have an H and a K, which are subgroups of G. And you say, to what extent can HK be a product of some sort? Maybe it's isomorphic to H cross K. And then you'd say it's an internal direct product, okay? But it turns out there's lots of other products too. So it turns out that DN is always a product between R, which we showed above as normal, and its flip, but it's not a direct product, it's something else called a semi-direct product, right? So there's other kinds of products when we get up to, in groups, right? So this is what's discussed in this section. Now this is all in the video up there, so I'm just going to sort of let that go. And then a little bit of stuff about semi-direct products here, and I mentioned the DN thing, and also here's where you can sort of see what happens with, not with ZPQ, but if G is order PQ, I can tell you what the answer is. There's two options. One option, these are P and Q prime, you know, P not equal to Q, right? So one option is that you just have ZPQ, right? That's the abelian option. The other option is that you have something like ZP, semi-direct product ZQ. This is where P is bigger than Q. And there's actually several different ways of forming the semi-direct product, but they're actually all isomorphic. So in the case that you have a group of order PQ, you've got one you've got one abelian group and it's cyclic, and you've got one non-abelian group that is not cyclic, right? And so that's sort of the situation there. Now, this is going beyond what you need to know in the class, so you can ignore it or you can look at it. I mean, so one of you is doing your project over some of this stuff, so you can look at it, right? Kind of knowing what happens with the DNs is nice. And like I said, knowing what happens with small finite groups is kind of nice. So that's the product stuff. Let me just show you one more thing in the notes that I kind of like you to look at. Let me see. So yeah, it's in this set of notes. So where do I have it in here? So in this mini lecture, where do I have this? Actually, this may be linked. Let me add a note. I'm going to add a link in the topic 3, so you don't have to go searching for it. Let me just point to it, and then I think I'll say I'll quit and let you go, unless you really want to see it. It's a cool theorem. I'll just sort of point to it. I talked some about group actions. Again, one of you is doing something like the CELO theorems or group actions. So group actions are really important for CELO theorems. The book only talks about group actions for the symmetric group, and that's really not what you should do. You should really just talk about actions on a set set X, right? So that's sort of what I'm talking about here. So I won't go through all this. Okay, I'll let you there's a video, right? I made a video for it. So I would suggest watching the video. There's a really nice result that I will let you use, but I'd kind of like you to at least watch the video. First of all, Lagrange's theorem just falls out of this stuff. But as an application, there's this Cauchy's theorem. In your book, you have Cauchy's theorem for abelian groups, but there's nothing special about abelian groups, right? So if I have a finite group G, and P is prime, and P divides the order of G, okay, you can always find a G in G where the order of G is P for any prime that divides the order of the group, okay? And you don't need the group to be abelian. Your book has a proof for this that is abelian groups. Here's a very short proof of this. It's really cool. What you do is you take G and you form a set X, which is the set of all X1 through Xn, such that XP, such that X1 times X2 times ... times XP equals E, right? And so, like, how big is this set X? Well, once you have the first P minus 1 things, there's only one thing you can choose for the last one. You take its inverse. That's all it can be, right? So you have complete freedom on the first P minus 1 thing. So this X has size of G to the P minus 1, right? And what you do is you let ZP act on this set by rotating, right? You just sort of, if I apply 1 to this, I sort of rotate 1. If I apply 2, I rotate by 2. Just sort of push forward by n, right? For n between 0 and P minus 1, right? Anyway, I'll stop saying anything about it, but you use this sort of interesting action. Okay. I can't really say much about it without going into all the details, but use this interesting action to show that you can find this element of order P, right? So the point is, so one element in this X, let me just say real quick, let me not say. I just won't say anything more. I'll let you watch it if you want to watch it. I think it's a really cool result. I think it's a really interesting little proof. I will say I stole this proof from one of the first videos in the visual group theory proof, where he's talking about the silo theorems, right? So it's one of the first ones there. But it's a really nice example of using group actions, which is not using the symmetric group. It's not using the SNs, right? It's using a general group action on a set X, where you just construct this really funny set to prove what you want. It's almost like magic. I mean, it's a really interesting theorem, I think. But it does give you the right to say that whenever you have a prime that divides the order of G, there's an element of order P in that group, right? So some of you could have used that for some of the things you did for the DQs, right? So you had this thing about a group of order 21, another thing about a group of order 15, right? In both cases, you know there's an element of order 3 and of order 7. In the 21 case and in the 15 case, you know there's an element of order 3 and order 15. In the 15 case, you assume the group was abelian, so you could have used the theorem in the book, right? But in the 21 case, you were not assuming that. So the theorem in the book would not have helped you there, right? But this theorem would. This theorem would work for you there, right? So anyway, I'll just leave it for you to watch, right? When you have some time. All of these videos are a little shorter than 30 minutes. I think most of these aren't too long. The video on products is very long. It's like 42 minutes. And I will say with that video, I'm just touching the surface of what products we can do with products. So someone else is doing wreath products, I think, or not wreath, braid groups. And there's this whole other set of products called wreath products. There's all sorts of products with groups. So products are very, very boring for vector spaces. They're very interesting for groups. The other place they'll be a bit interesting is when you get into 571 and you have products of topological spaces, right? So you will see products and quotients and things like that when you do analysis too, right? So they're not only group ideas, they're actually also analytical ideas. So very, very general sort of ideas here. Anyway, I think that's probably enough material for the day. So any questions about anything?
That
we can
link,
go just a little.
that link you're talking about, it's on there. Because I was looking at it earlier. It's orbit stabilizer theorem, and he says I have notes here and has a link right before
Where do I
external.
see it here?
Right before external internal products, right there, notes here.
Oh yeah, right there, right there. Okay,
Yeah.
there it is. Yeah, yeah. So take a look at that. It's a good. I really think that proof of the Cauchy's theorem is cute. I don't know. I think it's really worth. It's really not hard to think through. It just would be another 30 minutes of lecture, right? So I think watch it, think about it. It's kind of a cute argument. And if we don't have anything else, we can end 10 minutes early. We didn't have any glitches today. And you know what I did, I think, after going through and talking to my tech people? I think one of you suggested this. It may have been Shay. I plugged in the plug in the back of the monitor extra hard. And strangely enough, I think that was causing all the problems. So one of you said something about power getting to the monitor. And it wasn't quite that, but it was sort of related to that. So
Yeah,
anyway,
that was
all right.
that was me because I use an espresso tablet at work with my computer that's also plugged into like 3 monitors, and it kept glitching. And I looked it up, and it just they gave me an extra power cord, and it works fine now.
Yeah, so I don't think it was the power cord. I think that the actual plug into the whatever you call that plug going into the monitor itself, that was loose. That was causing the problem. Weird set of problems to cause, but that's what it was. Anyway, okay. If I keep talking, I'm not doing good at letting you go early. So I will let you go, and I will see you next week. And just write whenever you have any questions about the exam or anything. Okay.
Have a good week.
Okay,
All
thank
right, you guys too.
Thank you.
I just
Bye-bye.
wanted to check that you got my response for the project.
Who is talking?
This is Hannah Rossman, sorry.
Oh, and what was your? I may not
Um,
have looked since I talked to you last. So what was your decision?
Yes, the isomorphism theorems. I
Okay,
don't
so the
know.
one I just did.
So
So there are 3. Hold on, let me show you. So everyone else can leave, but I will show you. I've got some notes on those too. So let me go find them. Actually, do I have a link here? Let me see if I have a link here. Let's see. The thing I was just looking at was this. Let me open these up separately. Let me open these up. Oh, you know what? I may have had those in this set of, again, this may be in this set of, let me see. Let's see, because I talk about isomorphisms and topic 2. Oh, no, I don't have it there. Let me see if I have it here. So in topic 3, so I need to put this link. Let me find that. do I have this? Oh, that's what I have there. So I know I have this somewhere. I'm just not sure where. Now what am I doing? Am I so confused? Maybe here. I should definitely put a link to this page in what I was just doing. Let me copy this. Yeah, so here's homomorphisms. No, I don't have it here. Wait, do I? Don't. Oh, maybe I have it. Wait. Okay, maybe I have it. So I'm just trying to remember where I have this information. Maybe I have it in the ring. Some of my stuff about rings. Oh, here. So this is actually later on. This is the ring theory notes. So I have a lot of videos in here already. Here. So I have this stuff on first, second, third isomorphism theorem. So these are the three isomorphism theorems. And let me, so this is Hannah. So this is like, so you don't need to know this about rings. Let's see, let's see, can you access that?
Let me look.
It'll at least tell you what the theorems I'm talking about are, right? And then you can just talk about them for groups. So,
Okay.
so the first isomorphism theorem I just talked about, right? And then there's those three. And if you want to have fun, there's this funny Sawzenhouse butterfly lemma, which I just remember when I was an undergraduate. I don't even know how to spell it. Sawzenhouse butterfly lemma. So it's got this nice diagram, right? Oh, you can't even see what I'm showing you, can you?
Oh no, I can see it.
Oh, am I still sharing?
Yes.
Oh, okay. I thought I'd stop sharing. Okay. Yeah. So it's got this kind of cool diagram. Anyway, it's a funny theorem. There's no reason to have this now. It's just sort of an interesting add-on if you want to do it. But the first three isomorphism theorems are important. So if you want to just talk about those
Okay.
together with applications, I mean, again, as we go and we start doing rings, you'll see a lot more applications. So maybe it's a little hard to just figure out what those are now, but you can probably find some.
Okay. Could I use this as one of the applications and talk about this lemma?
Oh yeah, if you want to talk about this, I mean, this is just a fun lemma. Like if you were in a grad school that had a like exam to see if you could make it onto your PhD program or something like that, this is one of those weird things that you may be asked about, right? Because it's just one of those things that are talked about. I'm not really sure why. It looks cool.
Okay.
Yep. But okay, so that's what you're gonna do. So I'll put you in the list for that then.
Okay, perfect. Thank you so much.
All right. Yep. Talk to you later. Bye bye. Okay. Ich bin fertig. A bit early today. Oh, now I get